This video is about equilibrium expressions and calculations. It goes along with your notes. This has equilibrium expressions worksheet, and the notes are this first page here. So there's a difference between equilibrium expressions and the actual calculation to find your equilibrium constant, which is KEQ. KEQ is written as a capital K, lowercase eq. Okay. To determine the expression for it, we use a chemical equation. For here, my chemical equation, I just have a generic one, where I have A, which is aqueous, plus B, which is a gaseous state, is in equilibrium, told by our double arrow here, to make C a solid and D an aqueous solution. Okay? As I do this, I notice that I have coefficients in the front, shown by a lowercase letter, and my actual element or compound shown as my capital letter. I notice that I have multiple states, aqueous solutions, gases, and solids. To write my equilibrium expression, I write my concentration of the products raised to their coefficient divided by the concentration of my reactants raised to their coefficient. For multiple products and multiple reactants, I simply multiply this together and keep writing them, one against the other multiplied together, and same for my reactants. Now when I write my equilibrium expression, because I'm looking at concentration signified by the brackets here, those are moles per liter. Now a pure liquid and a pure solid, you cannot change the concentration of them. So if I have mercury, which is a liquid at room temperature, I cannot increase my concentration of mercury when it's the same thing. It's pure. I can't temper with that. Same thing if I have a piece of sodium chloride. Well, that again is a solid. I cannot increase or decrease the concentration of that solid. So since that cannot change as I go through a reaction at equilibrium, therefore only gases and aqueous solutions are going to be included in my equilibrium expression, and I will not have any solids and liquids. So as I look here in my expression or in my chemical reaction equation listed out, I notice that I have a solid for C. That means that when I write my equilibrium expression, I cannot have C in my actual equilibrium expression. So I write it out, my products raised to their coefficient, so D raised to its coefficient of D, divided by my reactants of A plus B, both raised to their coefficient. I do not write C in my equilibrium expression because it's a solid and I cannot change my molarity of my solid. Our equilibrium constant, KEQ, once we solve for it, can tell us information about our actual reaction. If my KEQ is greater than 1, that means I'm going to have more products than reactants. If there are more products than reactant, allowing my fraction to have a higher numerator than denominator, that means that my products are favored in my equilibrium expression, as is my forward reaction. In equilibrium expressions, the forward reaction goes to the right, and I always have my products on the right-hand side, my reactants on the left-hand side. If my KEQ is less than 1, that means that my denominator has to be bigger than my numerator. Therefore, I'm going to have more reactants than products, less products than reactants. My denominator will be smaller. Therefore, my reactants are favored, and a reverse reaction is favored. In other words, my reaction is going to proceed to the left more. So if you haven't done so already, take a moment to read through about your equilibrium constant, KEQ, which should be a review of what I've just stated. Then you get to the point where you write the following equilibrium expressions in each box, and you are given their actual reactions, and you're asked to write their KEQs in the boxes provided. 1A asks you to write the equilibrium expression for a reaction of O3, which is ozone, NO, which is nitrogen monoxide, is in equilibrium with oxygen, O2, this is not dioxide, but it's oxygen, plus NO2, which is nitrogen dioxide. Now remember that only gases or aqueous solutions can be written in our equilibrium expression, which we have, and they are all raised to their coefficient. In each one of these, the coefficient is 1. So I write KEQ is equal to my concentration of my products, O2 and NO2, divided by the concentrations of my reactants, O3 and NO. And I stop there. When I want to actually calculate KEQ, then I do my next step of putting in the numbers. Go ahead and try letter B. You should get that KEQ is CO2, the concentration of that, raised to its coefficient of 2, divided by CO, raised to its coefficient of 2, times O2. Now letter C, we have ammonium nitrate, which is a solid, is in equilibrium with dinitrogen monoxide plus liquid water. Okay? Again, I can only have gases or aqueous solutions in my KEQ, so I do not include ammonium nitrate, I do not include water, and I'm simply left with dinitrogen monoxide, so that's all I write. Go ahead and try letter D. For letter D, you should get your KEQ equal to the concentration of O2 times hydrogen squared, because of its coefficient, divided by water in its steam form, or gaseous form, raised to its coefficient of 2. Next, let's actually try to do some calculations where we calculate KEQ. Now again, there's a short bit of reading to read about that. And we are calculating our concentrations, or we're calculating our KEQ at equilibrium. So we're only dealing with equilibrium situations. Number 2 gives you a chemical equation written here, written at the beginning of that question. And it asks you to find the equilibrium constant given the concentrations of all 3 items present. Now sometimes you'll just get moles and you'll told how big the reaction vessel is, and you'll have to take your moles and divide by your volume of your container to determine your molarity. So for number 2, you want to start by writing down your equilibrium expression, which is PCl3 times Cl2 divided by PCl5. We plug in our given information, our concentration of PCl3 times our concentration of Cl2 divided by PCl5. You notice that your concentration of both of your products is the same here because they are at a 1-to-1 molar ratio. At equilibrium, they're going to have equal concentrations. You'll want to note that for later problems. When I plug these into my calculator, I get a KEQ equal to 0.064. Notice that there are no units on my equilibrium constant. Here, my equilibrium constant KEQ is less than 1. Therefore, my reactants are favored, as is the reverse reaction. So go ahead and do numbers 3 through 10, first writing the equilibrium expression, then pulling down your variables, solving for your missing information, and then determining if reactants or products are favored based on their KEQ value.